I'm going to get started. So hi, those of you who don't know me, I'm Mr. Knott. Welcome. So what I want you to do is I want you to open up the lesson template that we sent out previously. You're going to be working, if you can print that out, that would be great if you had a printed copy, but if you don't, it's okay. You can just take notes, but I'm going to be referencing that, the live lesson template as we go along. So I'm going to share my screen and we'll, just as soon as I admit everybody here, share screen. That's weird. Okay, so let's have a look. So this is the live lesson template that we're going to be working from. So first of all, just norms we've already gone over. Some of these, make sure that your name has your last name in it as well. Leave your video on if at all possible. Make sure that you stay muted. And finally, if you have a question throughout any of this, make sure that you raise your hand. That hand raising option is available. If you go to, again, the participants window, you should be able to raise your hand through there. Okay, so we're going to get started with the lesson. So we're going to begin by reviewing infinite limits, which was the topic of last week's work. And last week, what we did was we evaluated infinite limits basically numerically. So I just want to sort of remind you what an infinite limit means and how to evaluate it numerically with a couple of examples. And then later we'll see how to evaluate infinite limits without using a calculator, without using numbers, but rather doing it algebraically. So let's just start with this example here. Example 1, we have the function f of x is equal to 2 plus 1 over x. And we'd like to find the limit as x approaches infinity of this function. So just very quickly, let's recall what this means. This means the value that f approaches as x becomes very, very large. So what we do is we imagine that x becomes a gigantic number like 100, 1,000, a million, a billion, and we sort of ask what's happening to the value of the function as that occurs. And if the value of the function is converging to some particular number, then that's going to be the value of the limit. Now, one way to find this, as we saw last week, is to actually plug in a specific very large number. So, for example, to get a sense of what the value of this infinite limit might be, I can plug in a very large number for x, like say 1,000. So I'm going to go ahead and plug 1,000 into this function. I have f of 1,000 is equal to 2 plus 1 over 1,000. And I think as a decimal, that would be 2.001, 10, hundreds, thousands. Yeah, I think that's right. Okay, so I plugged in 1,000, and as you can see, as a result, I got something very, very close to 2, all right? That's telling me that the value of my limit is probably 2. Okay, if you plugged in something even bigger than 1,000, like if you plugged in 1,000,000, then you would get something even closer to 2. So that we can see as x is becoming a very large number, the value of the function is approaching 2. Okay, so the limit is 2. Okay. Well, with that in mind, let's move on to the second example here. We have a different function. It's f of x equals 9999 e to the x. And we'd like to find the limit as x approaches negative infinity. And because x is going to negative infinity, the meaning of this limit is slightly different than the prior one. So let's just sort of recall what it means. This means the value that f approaches as x becomes a very large negative number, right? So like negative 1,000, negative 1,000,000, negative 1,000,000,000. And just as before, we can sort of get a sense of what this limit might be by plugging in a specific, very large negative number and seeing what we get. This is what we did last week. So I'm going to plug in something really large. I'm going to plug in, let's say negative 100. That's relatively large. I could go larger, but let's stick with negative 100. So f of negative 100 will be equal to 9999 e to the negative 100. Okay, and we have to get some kind of sense of what value this expression has. Like, what is it as a number? You know, what would it be as a decimal? And to see what it is as a decimal, you probably need to use a calculator. So off screen, I'm going to go ahead and punch that expression into my calculator and get a decimal representation for what that is. So 9999 e to the negative 100, I get something a little strange. Here's what my calculator says. It says it's about 3.719 times 10 to the negative 40. It's a bit of a strange answer. And to interpret it, you have to remember what this business about the 10 to the negative 40 means. That's scientific notation, right? And what it's telling you is that the result is obtained by moving this decimal point here next to the 3, 40 spots to the left. Okay, so this number is like 0.00000, right? It's like 40 zeros or maybe 39 zeros and then 3719. So this number is extremely close to 0. In fact, for all practical purposes, it basically is 0, all right? And so we can see that x is becoming a larger and larger negative number. This limit is going to go to 0. And if you plugged in a larger negative number, like negative 1,000 or negative 1,000,000, you would get something even closer to 0. So certainly the limit of this function as x approaches negative infinity is 0. Okay, so that's a bit of review from what we did last week. And I guess I'll just maybe pause here and ask if there are any questions. If you have any questions at this time, raise your hand and I'll try to answer it before we move on to the next section. I see no hands. Okay, cool. So in the next section, we're going to take a few moments to just talk about some common fractional expressions involving x and what they mean, and in particular, what they mean in the context of infinite limits. So I'd like to talk about what happens as x goes to infinity and negative infinity for these three expressions here: 1 over x, x over 1, and x over x. So let's start with a here. And we're going to evaluate these infinite limits not by plugging in specific large numbers like we did in the previous two examples, but just by thinking about it, okay? So let's think about a, and let's try to analyze the limit as x approaches infinity of the function 1 over x. All right. Now, instead of plugging in a specific big positive number like 1,000, let's just think about what happens. As x becomes a really big number like 100, 1,000, or 1,000,000, what you have is something like 1 over 10,000 or 1 over 10 million. That is a very, very small number. And in fact, the bigger that x gets, the smaller the value of this expression will become. Okay, so this limit is going to 0. And one way of understanding that is that the denominator is growing to be very, very large, but the numerator is staying fixed at 1. So for large values of x, the numerator is quite small, but the denominator is very, very large. The overall value of such a fraction is going to be a very small number. In the second example, the x is in the numerator. Imagine plugging in a giant number like 100 or 1,000 or 10,000. You're going to get something like 10,000 over 1. Of course, anything over 1 is just itself, which means that as x gets bigger and bigger, the value of this expression gets bigger and bigger. It's not converging to any particular value. It's not settling down on any specific number. It's just growing without bound. We say in this case that the limit does not exist because it's not converging to any particular number, but specifically, it's going to infinity because it's just getting bigger without limit. And it's easy to see why that's true because the numerator is growing, whereas the denominator is not really growing. The numerator is getting bigger, but the denominator is fixed. And for C, we have the limit as x approaches infinity of x over x. I hope you recognize that x over x is just 1, right? So no matter what x is, as long as it's not 0, this expression is going to just be 1. So the value of this expression isn't growing at all. It doesn't matter what x is. The value of this expression is always 1. So the limit as x goes to infinity is 1. You can see the dogs have decided to start barking right now as we start our class, but that's okay. It's not my dogs, so I'm okay. Okay, so D, E, and F we'll do very quickly. It's the same expressions, except now we're looking at the limit as x goes to negative infinity. You know, if x becomes a really big negative number, this expression's still going to go to 0, right? Like 1 over negative a billion is still basically 0, right? So this thing's going to 0. E is slightly different, right? As x goes to negative infinity, as x becomes a larger and larger negative number, I mean, x over 1 is still just x, right? So as x becomes a larger and larger negative number, this expression itself becomes a larger and larger negative number. It's not converging to anything. It's not settling down on anything. So the limit does not exist, certainly. But we say that it's going to negative infinity, right? Because as x becomes a larger and larger negative number, the value of the expression is itself just becoming a larger and larger negative number. And then finally for F, I hope it's clear that once again, you'll just get 1. It's the same as C, essentially. Okay, so I think at this point, I will toss it over to Ms. Paget, and she will continue. So I'm giving you the host.
Great. Okay, so let me share my screen now too. So I'm gonna pick up where Mr. Knott left off on this worksheet. So on the next page, there's this graph. I'm gonna switch this around a little bit. We're gonna talk about the limits first and then have you think about the graph. So the graph is there, we're gonna talk about that in a second, but come down to the bottom first. So I want you to use what Mr. Knott just talked about to find these limits at infinity. So I want you to think about on each of these as x gets really, really big. So these 6 right here are the limit at infinity. So as x gets really big, what's happening to the function? Now we're gonna split this up to make it go a little faster. If you are one of Mr. Knott's students, I want you to answer the first 3. If you are one of Mr. Paniagua or Miss Alibai's students, I want you to think of the second 3. And if you're one of my students, I want you to come down here and answer these 3. And of course, my students, I gave the most complicated ones. So my guys, think about these ones. This one goes to negative infinity. This one is negative infinity, and this is negative 1 from the right. So think carefully about those. Those are a little bit trickier. So take about a minute, answer your 3 questions. So Mr. Knott's class is the first 3, Mr. Paniagua or Ms. Alibai is the second 3, and my class, bottom 3. You should have thinking music, like the Jeopardy theme. Dun, 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 dun. I won't sing. I won't punish you with that. Okay, so you're finding your 3 limits. I'm counting on you to volunteer. So if you feel good about any of your answers, I'm going to count on some volunteers to go through these. Okay. Let's start with the first set. So this is Mr. Knott's class. If you guys give me some volunteers. So what's the limit as x approaches infinity of the function square root of x? You can raise your hand. You could also probably just unmute yourself and shout it out. Or Mr. Knott's going to cold call you.
Don't make me, guys.
Anyone? Anyone?
Okay, I'm going to start cold calling. Nikki, you want to give it a shot? What's happening to root x as x gets larger and larger and larger, the limit?
It's going towards infinity, like positive infinity.
Yeah.
It sure is. Well done. So does the limit exist or not?
It does not exist.
Okay, so we're going to remember Mr. Knott just said does not exist, but we know what it's doing, right? So, oops.
Or it does exist. Or no, it does not exist.
You're right. Does not exist, but goes to infinity. So we know it's the infinity part is we know it's happening. Okay, Nikki, that was awesome. Thank you. Now that he did that, you saw it wasn't so bad, right? The limit as x goes to infinity of x. Hint,
Come on, guys.
Not that different. Aiden, I see a hand.
It does not exist and it goes to positive infinity.
Beautiful. Okay. And third one.
That would be does not exist and positive infinity still.
Beautiful. So you'll notice all 3 of those are going to infinity. So they're kind of doing the same thing, but you'll see in a second when we look at the graph, they're actually, not all infinity is equal, right? So we'll come back to that. Let's do these next 3. So Mr. Paniagua and Ms. Olibai, there are less of you. So if anyone else wants to help out, you're welcome to help out too. What's the limit? And again, you can raise your hand or you can just unmute yourself and tell us. What's the limit for the log function? Remember, this is saying 2 to some power is equal to this number. So 2 to a power equals a number. As the number gets bigger, what happens to the power? Anyone? Anyone?
Jamie?
Remember that Mr. Paniagua is here and he can cold call on you.
Yep.
Yep. Okay. Doesn't exist positive infinity.
Beautiful. I sense a theme.
Great.
Thank you, Jamie.
Of course.
Okay. Then we have our exponential function. So the limit as x approaches infinity of 2 to the x minus 1. What's happening with that one?
This one's also does not exist positive infinity.
Beautiful. Okay. Oops. Okay. This last one's a little bit trickier, right? So the sine function, what is the sine function? I'm going to watch my video screen. I want you all to show me with your hands. What does the sine function go as x goes to infinity? Show me what the sine function looks like. Right? As x goes to infinity, the sine function just keeps going like this. So what's the limit? Is it approaching a number? No. Is it approaching infinity? No. It just doesn't exist, right? So here our limit does not exist. We can't say infinity. Oh, sorry about that. We can't say the infinity part because it's not going to infinity. It just doesn't exist, right? So that's one is a little bit different than the others. My thing is cutting off. Okay, great. My students, make me proud. A little bit different. Now we're talking about the limit as x goes to negative infinity. So what's happening as x goes to negative infinity? Who can I find?
Infinity.
Infinity exists, does not exist.
Does not exist.
Okay, does not exist infinity. There we go. Copy and paste is a beautiful thing. One of the things my third grader has learned over remote learning, how to copy and paste. Okay, what about, this one's harder. What about the exponential function 2 to the x? So when we have our exponential function, what does that graph look like? You can think of the graph, or you could think of as x is getting really big, what's happening to this first term? This is negative. 2 to a negative exponent means that's like what? Anyone? Anyone? Amber.
It makes it into a fraction.
It makes it into a fraction, right? And so just like Mr. Knott was saying before, if I have 1 over 2 to the x, because we're talking again about a negative here, if I have a fraction, as x gets really big, that's going to go to 0. So this part right here is going to go to 0, which means the whole thing is going to go towards
-1.
-1. Awesome, thanks. You can't see that. -1. Cool. And similar thing on our last one, right? Logs and exponential functions are inverses. We kind of have a similar thing happening here. But now we're talking about the log function. So remember the log graph? Exponential functions have horizontal asymptotes. That's what's happening here. This has what? A vertical asymptote, right? And so as we approach that same -1 from the right, the graph is going like this, so it's headed towards anyone? Anyone?
Negative infinity.
Beautiful, negative infinity. And what happens when we say infinity or negative infinity? We say it doesn't exist, right? So it does not exist, but because of negative infinity. Okay, that was some good practice with limits. Move that over. Can you guys? There we go. Okay, these are good. I want you to think about these. So we said on all of these, I'm gonna stop sharing for a second. We said they all go to infinity. But Mr. Knott was just saying, like, we can find the limit if we think about, like, if we know the numerator or denominator is bigger. But if they're both going to infinity, like, isn't that the same? So we're going to do a little activity. We're going to go back to the graph. I'm going to share Desmos, but you have a graph on your page that has this picture. So we have 6 different functions here. What I want you to think about, and I'm going to put you in breakout rooms. I want you to think about which of these is getting bigger. We just said the limit for these 5 at least is infinity. Think about which one's going to infinity faster. So the slowest infinity to the highest infinity, they're not all getting there at the same speed. Does that idea make sense? So you're gonna rank them. You're gonna be like, this one's the slowest, this one's the fastest. You're gonna think about what you know about functions, and you're gonna use the graph, right? They're all graphed right here to help you. So you all have the graph on your worksheet. If you printed it in black and white, just take note sort of the colors, maybe on here if you have it on your computer screen. And I'm gonna put you in breakout rooms. Oh, all right, where are we at? People, I think everyone's back. Okay, so I need a volunteer to tell me how you ranked your functions at infinity. So as we're headed to infinity, which one, we're going from slowest to fastest in terms of approaching infinity. Volunteer, you can say my group said.
I saw Solomon raise.
All right, I got you. Okay.
All right, Give me slowest.
Slow.
to-
Oh, slowest to fastest. Oh, I want fastest.
You can go the other way. That's fine.
Okay,
I'm
slowest to,
adaptable.
oh, I'll go fastest to slowest then.
Okay, which one's
Fastest would be y equals x squared.
Okay, the green one.
Yeah,
Okay,
and then should I just keep on going?
go. Just keep going.
Okay. And then 2 to the power of x minus 1.
The purple one, if anyone did it by
Yeah.
color.
And then x equals y, or y equals x, sorry.
Yep, that's the same.
Yeah.
Yep.
And then log 2 x plus 1.
Okay.
And then root x. And
Okay.
then obviously,
And then
lots and
sine, right?
lots
We talked before about how sine just keeps going like this, so it's not going to infinity. So obviously it's the slowest. So I just rearranged these here on my screen from slowest to fastest. Do we generally agree with that order? Do we have any dissent? Anyone disagree? Anyone feel strongly about a different order? I'm seeing nods of no. I'm seeing some smiles, knowing that my goal is to trick you, right?
Wait, what did I do wrong?
Everyone agrees with you. You
Oh,
didn't do it
okay.
wrong. Everyone up here agrees with you, right? Ellis, right? You know there's a trick.
It's gotta be a trick.
There's always a trick. Okay, let's zoom out. Should we zoom out and see? So let's zoom. The beauty of Desmos. Okay, so this right here looks like that right there, right? Cool, so far so good. Move it over, move it out. I'm gonna move it over. I'm gonna go investigate over here what's happening with the orange and the black. Anyone? Anyone, do you see it? Ah, what happened? Desmos tells us what's happening or where it happens.
Alright, so like how was I supposed to know that? I'm confused.
You weren't. We tricked you.
Oh,
You
okay.
weren't. We tricked you, and not just you, all of you. Nobody disagreed. So what happens is over time, the square root function is actually going to grow bigger than the log function. And the place where that's happening is right here for these two functions. Okay, so those two swap. So let's swap those two. Okay, and then the blue one is right there. That's cool. And then let's see what happens over here with the purple. Uh-oh. This one is going to be a little easier to understand. So we're comparing x squared to basically 2 to the x. This says 2 to the x minus 1, but basically as x gets really big, it's basically 2 to the x. So when the base is small, 2 to a power is going to be smaller than that number squared, right? But then we hit this sort of magic number. Think of 2, 4. What's 2 to the 4th power? 16. What's 4 squared? 16. That's kind of that magic number. The reason why this is not 416 is because our function was 2 to the x minus 1. So there's a little bit of a shift in there. But basically that 2 to the 4th, 4 squared, is where the exponential function starts getting bigger. And we know when we did exponentials back in the fall, exponential functions, remember if you invest money, how fast it grows when you get over a long period of time, or populations, how fast they grow. So the exponential function for these functions after this point is going to take over. So in the long run, it's going to grow faster. And that's going to be true for all exponential functions, are going to grow faster than what we call these are power functions. So exponential functions are growing faster. So let me just swap those. Okay, don't feel bad. It was sort of designed to trick you, to make it look as if that's what's happening. But just thinking about understanding why they swap. By the way, remember at this point, I was saying that 416, which is basically that point. Look at these two. Does it make sense to you why it's the same number in reverse? Tell me about these two functions and these two functions. So x squared and square root of x.
They're just the reverse
They're
of each other.
inverse.
They undo each other.
Yeah, they're inverse functions. So here we're intersecting two functions, and here we're intersecting those two functions' inverses. So it also should make sense to us that whatever's happening here is the same thing that's happening here because they're just reflections of each other. Okay, so what we got here is sort of this hierarchy of how functions are growing, right? And so they're all headed to infinity, but some of them, the exponential function, right, is growing faster than the power, which is growing faster, which is growing faster, right? So we sort of have this hierarchy. So I'm gonna toss it back to Mr. Knott for the very end of our lesson. We're almost done. You're doing awesome. To finish out with our examples. Mr.
Cool.
Knott.
Hi again. Yeah, so remember, like the overall objective for this lesson is we want you to be able to evaluate infinite limits without plugging in numbers. Like we want you to just be able to look at it and sort of look at the functions involved and say, this is what the limit is. And the key to doing that is this hierarchy of growth. It's this hierarchy of which functions grow the most quickly and which ones grow the most slowly. We'll see why that is in a second, but for now I just want to make clear what the hierarchy is. Which kinds of functions grow the most quickly, which ones grow the most slowly, and so on. And I've got this right here, which I want you to copy down into your notes. It's at the top of this page here. What I have is 3 families of functions. So in the first family, these are the slowest growing functions. They're functions which don't really grow at all. We have constant functions like 5 or 12 or 7. Those don't grow at all. They just stay the same. And also in that family of the slowest growing functions, we have sine and cosine, because as we've seen, those don't really grow over time. They just oscillate. They bounce up and down. So these guys, constant functions and sine and cosine, this is the slowest growing family of functions. Then we have the second family of functions, which is basically powers of x. Sometimes they're called power functions. So x to some number, like x to the second or x to the third, those are all power functions. And what I want to emphasize is that within this family, within this family, we have included not just polynomials like x squared and x to the third and stuff like that, but also root functions like square root of x or third root of x. Because remember that roots are really just fractional powers of x. So like square root of x is actually just x to the 1/2. So all those root functions are actually in this family. And within this family, the ordering within the family is determined by the exponent, right? So what I'm saying here with these less than signs is that this guy here, the x to the 1/2, grows more quickly than x to the 1/3. And plain old x, which is like x to the 1, grows more quickly than x to the 1/3, and x squared grows faster, and x to the third grows faster still, and so on. And then finally, we have my third family of functions, which is the fastest growing family of functions. These are the exponential functions. These are functions where the variable is inside the exponent. And as you can see, within this family, the ordering is determined by the base, which is like the number on the bottom here. So 3 to the x grows faster than 2 to the x, and 4 to the x grows faster still, and so on. A special example of this that comes up a lot is e to the x. Remember e from way back when? It's like this funny number. E is just like a constant. It's like 2.7 or something, I think, 2.71 or something like that. So e to the x is actually in this family. I guess it would be between 2 to the x and 3 to the x, because e is like 2 point something. So that's an important example as well. Maybe you noticed that I didn't include logarithms in here. They do have a role. Logarithms are actually slower growing than the power functions, but in the examples you're going to be doing in this worksheet, you won't be looking at any logarithms. terms. So this is a slightly simplified picture, but and you know, I really want to emphasize before doing the examples, like what this hierarchy is telling you. If I take two functions, so here's just an example. I'm going to take a really fast growing power function, okay? And I'm going to compare it with a really slow exponential function. So here's a fast power function. Like, how about, let's say x to the 100, like x to the 100th power. That's a really fast growing power function, right? And if you like, you can even put a really big coefficient in front of it. Like I could put like a 999 in front of it. That is a really fast growing function. If you graph that thing in Desmos, it's gonna look like a vertical line. It's really fast. Now I'm gonna take a comparatively slow growing exponential function, okay? So if I want a slow exponential function, that means I want the base to be smaller. You still want it to be bigger than 1. If you think about it, 1 to the x is actually just constant. But if I take something like 1.01 to the x, that's an exponential function, but it's very slowly growing. If you graph that thing, you'll see it's almost like a horizontal line, very, very slow. But I want to emphasize that even though this is a super fast member of the power function family, and this second guy here is a super slow member of the exponential family, nevertheless, can you give me a guess about which one grows faster as x goes to infinity?
The 1.01 one.
Yeah, thanks, Rex. The exponential function grows faster. Eventually, this thing will catch up. It will take a long time. Like you might have to go out to x equals 1,000 or 1,000,000 or something. I don't know. It'll take a long time. But eventually, this one will catch up. And not only will it start beating this other one, it will smash it into the dust. Like for really big values of x, this function is going to be so much larger than this other function that this little weak power function compared to this exponential function, it's almost like nothing. Okay, and recognizing that comparison is really key to analyzing infinite limits, okay? So anyway, the exponential wins. So let's move on to these examples, and now let's finally talk about how to evaluate infinite limits algebraically, just by analyzing what kinds of functions do we have. So usually, I'm reading here, we want to evaluate infinite limits of functions involving fractions. To do this, just eliminate all terms from the numerator and denominator except those which grow the most quickly. So we're going to do that, and I'm going to explain why that works as well. Let's have a look at the first example. So we have the limit as x goes to infinity of this complicated expression. Now, what I'm going to do is in the numerator and the denominator separately, I'm going to ask which of those terms grows the most quickly. So let's start with the numerator. I've got these 3 different terms, 5x to the 4th, the cubic term, and the constant term. Which one grows the most quickly? Layla, you just happen to be on my screen, so I'm cold calling you, sorry. Which one grows the most quickly?
The 5x to the 4th.
Yeah, it's a power function. It's, you know, I mean, this is a constant function. It doesn't grow at all, right? It's the power function that's, you know, got the highest exponent. That's going to be the one. And here's the idea. When x is really big, like really, really big, this term is so much larger than the other terms that compared to this term, they're nothing. You can basically ignore them. For really big values of x, this term is basically the entire numerator. These terms are nothing compared to the 5x to the 4th. So for sufficiently large values of x, the numerator is very well approximated by just 5x to the fourth. That's the term that dominates the numerator, okay? Same thing, in the denominator now, we make the same analysis. We just ask which term grows the most quickly. Well, this is some stupid constant term, right? That doesn't grow at all. This is a cosine function that just doesn't even really grow, it just sort of oscillates. But this thing, that's really properly growing, right? And for sufficiently large values of x, this guy is going to be so much larger than the other terms that you can just ignore them. I should really say that this is approximately equal to, I should really say that this is the same thing as the limit as x goes to infinity of this. Now, here's the payoff. Like, why is it worthwhile to sort of drop the slower growing terms? The reason why is that with this simplified expression, we see it and we can actually simplify it quite a lot. With this expression, we can cancel the x to the fourths, right? The x to the fourths cancel from the numerator and denominator, and this is just 5/6, which is the value of the limit. So in other words, if you plugged a giant number into this expression, like if you replaced x with 1,000 or something, you would get something very close to 5/6. Okay. Let's go to the second example and let's evaluate this limit. So here we've got the limit as x goes to infinity of 3x squared minus 2 over e to the x plus 4x to the sixth. And once again, all we have to do is just look at the numerator, ask which terms grow the most quickly, and keep only the fastest growing term, and same thing at the bottom, and we sort of go from there. So looking at the numerator, obviously in the numerator, the term which grows the most quickly is 3x squared, right? The constant term isn't growing at all. So forget about the constant term and just look at the 3x squared. In the denominator, we've got this e to the x term and the 4x to the sixth. 4x to the sixth is pretty quickly growing. It's a quickly growing function. But this exponential function, as we know, is going to crush it. Like for really big values of x, e to the x is way bigger than 4x to the sixth. And so the denominator is basically just e to the x. Okay? Now, unlike in the previous problem, there's not really any simplification we can do. Nothing cancels in this expression. But I want you to think carefully. As x becomes really, really big, okay, it is true that both the top and the bottom are getting bigger. That is true. But the denominator is getting bigger faster. Therefore, for very large values of x, this fraction will be basically what? Who can tell me?
It would be 0.
It's gonna be 0. Yeah, why?
Just because the bottom is part of the third family that's so much larger than the second family. So it's going to be like when you get to really large numbers around infinity, it's going to be that much larger that it's just going to be like a really small fraction.
Yep. I mean, like both of these things are going to be big, but the denominator is going to be way bigger. It's going to be like, say, 1,000 over 100 trillion billion, right? That's basically nothing. So this is going to 0 because the denominator is growing faster than the numerator. Cool. And then one more. So now we have limit as x goes to infinity, 3x to the fourth minus 2x over 100x to the third minus 7 cosine x. We do the same analysis. We just ask what grows the most quickly in the top. Well, that's 3x to the fourth, right? And what grows the most quickly in the bottom? That's the 100x to the third, right? After making that simplification, hopefully you notice that we can actually simplify a little bit further, right? There's some cancellation between the x's. And after cancellation, that's going to leave us with limit as x goes to infinity, I think just 3x over 100. Okay. Now here's the question. As x gets really, really big, what's happening to the value of this expression? Anyone want to tell me about that? I will cold call if I have to. Let's see. Sam Donahue, what happens to the value of this expression as x gets really, really big?
As x gets larger, the expression gets like greater. It gets closer to positive infinity.
Exactly. Yeah, it's going to infinity. Like, it's not converging to any number. It's not getting closer and closer to 2 or 5 or anything like that. It's just getting bigger and bigger, right? So actually, I should say does not exist, and then in parentheses infinity, right? So yeah, exactly. So look, guys, just really quick summary as kind of a broad, outline here. In the first example, the numerator and denominator were essentially growing at similar rates, right? The fastest growing term was an x to the 4th term in the numerator, and an x to the 4th term was the fastest growing term in the denominator. And then we got, as a result, like the ratio of the lead coefficients, sort of interesting. You might remember that from last week. And number 2, ultimately, the denominator was growing faster than the numerator, therefore we got 0. And then in the third example, ultimately the numerator was growing faster than the denominator, so we got infinity. Okay, so that's kind of a quick summary of how all of this works. Okay, that's it, guys. So you are going to be receiving the worksheet for this week. That is all you have to do for the remainder of this week. Coming to this session was part of your 3 hours for the week. It's not like we had you come do this and then another 3 hours of work or anything. So it's just the one worksheet. I think we are all set, but if you have any questions, feel free to stay. We will answer them, but otherwise, we are good. You guys are good to go.